Okay then, so before I go into how we can get this sort of category, which we could call e to the power of a, where a is a small category in the topos e, and we're kind of thinking of a category of functors from a to the base category e. Let's start by recalling how we can think about the ordinary kind of category of functors from some category A into set. So a functor Z from A into set. Well, we can describe this in terms of actions. Okay, so for a element of the domain of F, sorry, for an element of Z of the domain of F, so the domain of F is just an object of A, doing Z on it gives this set, and then for a element X in this, well, we can do Z of F on that. We can do this lifted, this lifting of F to give this function Z of F. We can apply that to X to get Z of F of X. And that's going to be an element of Z of the codomain of F. But we can formalize this idea with an action. So we can think of a left action alpha, and it sends F comma X to what we call alpha of F comma X. And that's just defined to be Z of F operating on X. Okay. And that's going to be a member of Z of the codomain of F. Now, this action has some properties. In particular, we have that alpha of ID and X, so doing the action on the identity in X gives us X, because doing Z on the lifting the identity under Z and doing this function on X gives us X back. And also when X is in Z of the domain of G, we have the alpha of F after G operating on X is alpha of X comma alpha of G comma X. Okay, so this is like composability of functors. So what we want to do is basically sort of generalize or formalize this kind of idea, but we want to be able to do it for not stuff that's necessarily going on in set, but stuff that's going on more generally. So here's the idea. For a small category A in a topos E, what we'll call a functor zeta, I should maybe call it zeta comma S really, from A to the base category E, well, it involves a naught indexed family of objects. So we can think of this as an arrow S from zeta to a naught. Now, the idea here basically is that like, well, I think I introduced some useful notation at some point. Yeah. Well, let me just try and describe it. Directly. Okay, so in the last example which we looked at, we'd say, well, we have this functor Z, which we said is going to be a functor from A to set. Now, what that means then is that for an object theta of this category A, we're going to have that z of theta is going to be a set, okay? And so this thing z, I mean, we're really thinking of it as a kind of, in this context, we're thinking of it as a set z of theta for every object theta of A, together with this kind of action, which represents how these sets sort of morph into one another when one operates, when one does the kind of lifting of the arrows of the functors on them. So Z itself has all this information. It has, you know, Z of theta 1 and Z of theta 2 and Z of theta 3 and so on. So for any theta, which is an object of A naught, there's going to be this kind of collection of stuff. So what we could think of it as, we could say, well, we have this arrow S from zeta to A naught, and then for a point of A naught, so let's say a point y of A naught, well, then we can think about the pullback of y along S, and that's going to be a collection of stuff in zeta, and we can think of that as well, okay, no, I shouldn't say y. Let's say for a point theta of A naught, we can think of Z of theta as the pullback of theta along S. In other words, this is the collection of stuff in zeta which got sent by S to theta. Okay, so we're thinking of Z really as a kind of A naught indexed family of objects, okay, because we've got a family of objects for theta 1, which we call Z of theta 1, a load of object. We've got a family of stuff for zeta 2, that's the stuff that gets sent to zeta 2, and so on. I'll make this more clear. So, like, if we take the union Z of theta 1 union Z of theta 2, blah, 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 over all the objects, we get all this. So this is the union of Z of theta I over all the theta I in which are objects of A naught. Then let's call that zeta. And then we can suppose that we have this, well, we can, in this context of sets, we can think of it as a function, but this arrow s from zeta to a naught, which is such that z of theta I is equal to s to the minus 1, or, you know, the inverse image under s of this point theta I in a naught. Okay. Yeah, so that's the basic idea. But, you know, we want to now generalize this beyond thinking about sets. So for us now, this kind of functor, at least the objects going on it, are is represented by this arrow s from zeta to a naught. And like I say here, we can think of this as a kind of generalized set, s to the minus 1 of theta, for every theta in a naught. And as well as this, we have an action. Okay, so this action, it is going to be an arrow from the pullback of d and s to zeta. So, in other words, and this is just an expression for the pullback. So what we're saying is that whenever we have an arrow f, which is an arrow of the small category A, and we have this x which is like so this x here is like, it's like a member of one of these z theta i's, which theta I, which so x, sorry, is like you know, when we do this in set, for example, this functor, it'll like have a set z of theta 1 for object theta 1 of a, and a set z of theta 2 for object theta 2 of a, and so on. But we're kind of bundling all those together to be this object zeta. So then x is an element of zeta, but which of these kind of what type is it, you know, what kind of internal type does it have? Is it one of the sets which was does it, well, I mean, if we're dealing in set theory, then would it belong into one of the sets that came from doing z on theta 1 or from z on theta 2 or whatever? Well, the answer to that would be what is the value of Well, the answer to that is S of X, okay? Because, I mean, we have, like, zeta is like all, I mean, in set, for example, it's all of these, we've got like Z of theta 1 and Z of theta 2 and so on, but all kind of union together. And then we think of these as sort of fibers over over S. So we have this arrow S that's taking these into these objects of A naught. And then if we have some X in zeta, then if we do S on it, that gives us the object which this is a kind of fiber over. So it kind of tells us this is like the kind of internal type of X. This is like, for example, in a graph, is this element an edge or a vertex? Well, S would tell you that, okay? Okay, so this is kind of internal notation for this pullback here. Where we want to think about basically the collection of arrows F, where we can do the F action on X. So we want to have an arrow like F in A, and we want to be able to think about what happens when we do this F action on this element X of zeta. So that might send us to, like, if we're talking about a graph, that might be like finding the source vertex of an edge or whatever. So it might send us to a different Z theta n set. So in order to be able to do this action, which we now denote as AC instead of alpha, we want the kind of internal type of X to be the same as the domain of this arrow F that we want to use for our action. Okay, I should probably draw it like this actually, so it all matches up. Yeah. Okay, so this is the collection of stuff, and then that action just sends this back into zeta. But we want to have different conditions on this action. Firstly, when the domain of our arrow F is equal to the kind of internal type of this X, then we want to have the type that we get after we do the action on F of X is the codomain of F. Okay, so that makes sense. Secondly, we want to have that when the sort of internal type of X is equal to a particular object's star, then we want to have it doing the action associated with the identity arrow of star on X just gives us X back. Okay, so doing ID arrow does nothing. And thirdly, we want to have that our action respects this kind of composability like the functors. Okay, so we want to have that when the sort of internal type of X is that of the domain of G, and the codomain of G is the domain of F, then we want to have that doing the action using F after G on X gives us the same result as doing the action with F on what we get if we do the action of G on X. So there we have it. That's the description of how we can set up a kind of functor from this small category A to the base category E. So these kind of functors basically constitute the objects of this category E to the A that we're trying to cook up. What about the arrows? Well, they're going to be natural transformations. So firstly, let's just recall how natural transformations can be described in terms of arrows. Okay, so again, thinking about set, a natural transformation phi from this functor z from A to set to this functor z dash from A to set is going to be such that for each arrow f from L to R of A, and for each for each x with an internal type L, we have that this square commutes. So the long shot of this is that we're going to have the alpha dash of f at phi x that's this way around, equals phi of alpha of f of x. And I mean, here I should maybe put the subscripts on these components of a natural transformation, but I'm trying to get away from that, because in this thinking we're trying to do about actions, we're kind of thinking about all of the elements of these different internal types kind of bundled together. And so we just want to talk about how the natural transformations respect the domains and codomains of the stuff properly, and then we don't have to think about it all separated out into components. So then what's a natural transformation? Well, suppose we have a functor kind of like described by zeta and an s and action of s. So this is one functor from A to E, and here's another functor W from A to E with this action W. So then a natural transformation V is going to preserve the internal type, okay? So what that means is that for an x in zeta, if we have that its type is theta, so we have that s of x equals theta, then if we apply this natural transformation, we get v of x. So that's where this element of zeta gets, or thing of zeta gets sent to under v. So again, we're talking in the Mitchell-Benerbau language now. Well, we want the type of that, so that's now in this new functor. So w of that is also going to equal theta. Okay, so this is saying that the natural transformation preserves the internal type. And the only other thing we need is that square commutes. Okay, so basically this is like a kind of naturality condition on arrows, but what it's saying basically is that if we have this x in zeta, well, suppose it's ready to be acted on it's ready to be acted on by this arrow f. So its internal type is the same as the domain of f. Well, that implies that if we do the s action on it using f, so we get action of f comma x, and then we do the natural transformation on that, then we're going to have the same kind of result as what we get if we first apply the natural transformation and then do this f action, but now under this sort of second functor w. Okay, so if we have a look at this condition, so basically what it's saying is that when x has the appropriate inner type for x, doing the f action after doing the natural transformation is equivalent to doing the natural transformation after the f action. Okay, so if we have a look at this and we compare it to this, we see it's basically the same. Okay, alpha dash here represents this action after the natural transformation. I mean, of course, there's other ways to describe this. Like, for example, we might want to, if we're using our usual kind of functor notation, we'd write this as f of x of z. But anyway, yeah, so this is basically it. Then the idea is just that e to the a has as objects these functors from A to E, where each such functor corresponds to a sort of arrow like this that's ascribing the internal types together with an action which satisfy those conditions, and then so these become our sort of objects of this category, and this is a standard category. Okay, it's not a small category, it's not something which is sort of inside the topos. It's too big for that, but it is a category. And then the arrows of this thing are these natural transformations V. So we have these, and I mean, like, for example, the category of graphs we can now think of as something in sets. Well, for the category of graphs, we're going to give a set with this category here, but this now is just one view of the category of graphs as constructed using the topos of sets. Now, I am a bit confused about something, which is that, let's say you were dealing with, I don't know, say the category of smooth spaces, and then you want to sort of make graphs over that. So I suppose you can model, or I presume you can model this category inside the category of smooth spaces. You know, as one of these kind of internal categories, and then you can do this kind of internal construction of this kind of thing. But you can also make this kind of externally, because, well, I presume you can, because you can get your category of smooth spaces. That's just a category, and you can get this category of two parallel arrows, and then you can think about the exponential object associated with that. And are those two things going to be isomorphic? I'm just thinking aloud. I actually wonder if you can construct this in CAT using exponential objects. Maybe that only works for small categories, but I imagine this should work similarly, and I imagine you can do that, and I imagine these should be isomorphic. And then, of course, but you know, the point is that you can make these kind of things internally, and then once you've got them, you can do stuff like there's a needle lemma kind of generalized for this context, so you can do all your nice reasoning about stuff from there, and this is always a topos. So I have a video on category of pre-sheaves where I show how you can find all the topos machinery when it is set, but you can do that more generally when you start with any topos.